Hey, Mr. McLaren here. We're going to be going over drawing free body diagrams. Essentially we're looking at all these different forces and we're trying to figure out how the object's going to move. And typically this is looking at things with forces going sideways and straight up and down. If it's set up like that, it's essentially you're doing things on your x-axis and then things on your y-axis. Pretty straightforward. So you should do this reading at this time, so you could pause the video, do the reading, and then we'll get going on this. So for different forces here, we've got like the force of gravity, which is down below our force of gravity. I like to do F and then G. This is also shown sometimes as just W. You sometimes see that. I don't like doing that way. I like to always have my forces have an F on it. The normal force is like so, and then an applied force, I think that's just F, and then friction is oftentimes shown like this. I just want to double check what I've done, what the other symbols were for these guys, because I do believe it's worth showing you guys, because it's a little tricky. A lot of people oftentimes forget what's what, and then they see a problem, they're like, I don't know what to do here. So this would be sometimes just written as a big N, but then that's confusing because that's newtons, right? So I don't like doing that. Oh, sorry, this is not the right thing. So force of friction is I think that's mu right there. It's a Greek letter. Also, sometimes it's just written as a lowercase f. Either case is fine. To be completely honest, it's like not a big deal. I like to always have capital F's because that's the variable that we write for forces, right? So that just kind of makes sense to do that way. Okay, so we got all that set up, and then here's the fun part. You're like, oh god, this is not going to be fun. I know. I'm here at like almost 6 at night, so trust me, I feel the pain. A book at rest on a tabletop. So this object, it's not really being pushed sideways, or it's not getting anything pushing it sideways at all, but it does have gravity pulling it down. And if there was no table, it would fall down, but the table's pushing back with an equal and opposite force. So the object does not accelerate, it doesn't start moving, it stays at rest. So the object here, we can draw that right here, and then we've got these equal and opposite size arrows. It's really important that these are equal in their size, or approximately equal in their size, because we need to show that they're canceled out, that there's no net force here. So we got our force of gravity and what we call our normal force, which is essentially, well, it's normal because normally the ground is pushing up on you, preventing you from falling down. If, for example, something's not able to provide enough normal force, you will fall through it, right? So if there's something, a table, and you try and stand on it and it can't provide enough normal force, it's going to collapse. You're going to start accelerating, essentially. Yeah. So that's basically how this works. We're trying to show arrows that show the relative size of force as well as their directions. So always, if you were talking about on Earth, you're going to have some gravity. If you're out in space, it might be a little bit different. The forces of gravity will be very weak, and you can kind of just say it's not really there because it's so weak. Okay, so if we're looking at a student rests a backpack on their shoulder. The pack is suspended motionless by one strap from the shoulder. So we've got this backpack. Instead of drawing a little backpack, I'm just going to do a box. This object is motionless, which means it's essentially not got any net force on it. So it's being held up by the strap, and then we've got gravity pulling it down, but they should be canceling each other out. Got equal and opposite forces there. This is force of gravity, and then this is the force of the strap, or the applied force sometimes people will just write F for that, but I like to usually notate what's what when I'm doing these types of problems. It just helps me keep track of the parts of the problem. So there's a car stopped at a stoplight. Okay, this one's kind of interesting. It's, if it's stopped, that means that the forces are kind of canceled out. So we got force of gravity and the force of the strap, or not strap, force normal in this case, because it's the ground pushing up on the car, or the car would fall through it. And then it kind of depends on how you look at this. And if you look at this, we've got, if you've ever driven a car, which I know you guys are a little young to have done that, or if you've ever done like a go-kart or anything, you kind of know when you take your foot off of the brake, the car idles forward. So there is a little bit of force of the engine at any time if a car is on. So we've got the force of the engine, so force engine here, but it's being canceled out by the brakes and some friction. So friction will basically resist you trying to move. So we've got a little bit of maybe we make it like that tall, and then this one is a similar size, because these two, if you added them up, would give you that. So we've got our force of friction, and we got our force of the brakes. So we got force brakes, force friction, and those cancel out with the force engine in the x-axis, and then this cancels out on the y-axis, so this object, it will not move. Yeah, that's basically it. This one, you could think of it as just up and down, but in reality, there's this engine and the brakes and a little bit of friction stopping it from moving, canceled out. This guy right here is kind of weird. I was looking at this and I told myself last year I was going to get rid of it because it's a little bit confusing, but you're going to see it in high school, so it's worth at least talking about. So let's say we've got some object on a sloped incline. Gravity wants to take it down. So gravity is going to be like force gravity here. And in reality, that's got these forces in the x and y axis that are kind of making it want to slide down. And then also this is canceled out by the normal force. So this is the force of gravity in the y-axis and the force of gravity in the x. So we've got force of gravity in the x, and then we got force of gravity in the y. And this force of gravity in the y is being canceled out by the normal force of the slope pushing back up on this, preventing it from falling through the slope. And then this will have some friction that's canceling out that force of gravity on the x-axis. Again, this is much more like a high school problem that you would see with physics. You wouldn't really see this or be expected to do something like this in middle school. There's a lot going on with like breaking up a force into its x and y components, but at the end of the day, this object is not sliding, it's preventing from being sliding, so things are being canceled out. That's the takeaway from these problems. Let's see, a hot air balloon is held down to keep it from accelerating upwards. So we got an object, and it looks to me like we've got some force of gravity, and then this opposite force of the balloon, it's got like what we would call a buoyant force. Where it's trying to raise up because it's less dense. So we've got force of, I'm not really even sure what it's called, because it's not the force of the balloon. I think it's the buoyancy force is what we would call it, or something like that, where it's trying to move up because it's less dense than the air that's around it. So the other dense air is going to kind of collapse underneath it, and it's going to get pushed up until it's not where the air is so dense. So yeah, we've got those equal and opposite forces canceling it out. It's not moving. Oh, actually, hold on. I did this one wrong. This one is going to have some rope holding it down as well. So it's got like that force of gravity, but it's also got like some rope. So we got this force of this rope, and that's being canceled out with the force of the hot air balloon trying to rise up, or that buoyancy of it. It's kind of like how a boat floats on water, right? It's if that buoyancy wasn't pushing up on it, it would just fall into the water and it would accelerate downward. So you need something like it trying to get to the same density air to push it up, or same density, because a boat is actually less dense than water. That's why it floats. I know it's kind of weird to think about metal boats, but they have a lot of air in them. It's kind of weird. Okay, so you and your friend are helping push a stalled car out of the street. So we've got some car, because it's stalled. It's not got any engine, but it definitely has force of gravity here. And the normal force preventing it from falling through the road. And then you guys are pushing this, so maybe it's accelerating. So most likely, compared to the force of gravity, you're going to kind of have a small force, because it's a really heavy car. It's a car, right? You're not going to push that much compared to how heavy it is. So this is that force of the push that you're doing. And it's kind of unclear if it's accelerating or not, and how this is worded. So I would say this is accelerating. As you push the car, it's kind of gotta move slowly, and so it starts off kind of moving slowly and then accelerates and gets going fast, or faster at least. There might be a little bit of friction as well, but I mean, there will be some friction, but if it's accelerating, this is bigger than that. If it's not, the force of friction and push are canceled out, essentially. So yeah, that's basically what we do with force diagrams. Again, I would not expect you to be able to do these more complicated ones, but you should definitely be able to recognize, oh, this object's not moving. So the arrows should be equal and opposite. It's just like the net force calculation. If it is moving where it's accelerating, there's unbalanced forces. So I think all of these, they cancel out actually, don't they? Unless we're talking about this one where it's accelerating. So it's kind of going in that direction. It's accelerating in that direction. Yeah, so I think that's about it for force diagrams. Or free body diagrams is what we've called it on this worksheet. Thank you for joining me. I'll see you in class.